So welcome to our introduction to periodic functions here. For this note, I've given you the PDF with most of this stuff already on it, so you don't have a lot to write down, which is kind of nice for you guys. We're going to start with the fact that a function is periodic, so periodic, if it has a pattern of y value that repeats at regular intervals. So you've got like that stamp, and you can take that stamp and just slide it left or right and stamp again and just get that same pattern happening over and over again. One complete pattern is called a cycle. So I know in physics some of the terminology is slightly different than what we use, but for us the repeating pattern itself is the cycle, and the cycle can begin at any point on the graph. It's just you've got to get one complete pattern in there to be one full cycle, and that would represent the stamp that you would pick up and then slide to the left or to the right and stamp again. So I've got in my example down below a couple of different cycles highlighted. So here I started at a max and completed the pattern and ended at the max, and then I would be repeating that same W-shaped pattern over and over again as the stamp. But it doesn't have to be that way. I've highlighted another pattern over here starting on the x-axis, heading up and making this kind of shape, so kind of an M shape there, and to the left and to the right of that you've got your other M shapes happening there. So it doesn't really matter where the cycle begins, you just have to have one full complete pattern to make that work. Now what's important though is the horizontal length of one cycle is called a period. So we need to make sure we have that figured out. I think in physics they often represent that, instead of calling it the period, they call it the cycle. But like the horizontal length in physics is called the cycle, but we call that the period here. The horizontal line that's halfway between your highest and lowest point is called the axis of the curve, or the axis of the function. This one's not really a curve, so I didn't put the word curve there, but usually we call it, when we get to our sinusoidal functions, the axis of the curve. Now its equation is y equals the max, and I see that the plus sign did not get translated here. That should be a plus sign in there. The max plus the min divided by 2. It's halfway. Think of this as midpoint. And remember when we did midpoint, we added values together. It's like the average or the midpoint. We add the values together and divide by 2. Midpoint or average of your max and mins. Okay, so just keep that in mind. So in this case, for this particular example, we could figure out where that is. The periodic function has a max and min y value, then the amplitude is think of length, the difference between two values. So your max minus your min is that distance or the length, and then cut that in half. That can be thought of half as, oh dear, I can't speak today. This may be thought of as half the height of the cycle. So let's look at these particular things for this particular example. So in this example, the period is the length of one full cycle. So if I look here to here on my diagram, I'm going from 1 to 5. That would be a length of 4 units. Or if I look from 10 to 14, that's a length of 4 units. So our period is 4 units long. The max in this case is 2, and the min value, so the highest it goes is 2, the minimum it goes to is -1. So our axis of the function is halfway between those two things. So if we take those and add them together, so 2 plus -1, and then divide that by 2, 2 plus -1 would be 1, divided by 2 is a half, or you could say the equation would be y equals 0.5. So it is a horizontal line, and it's always in between, halfway in between the max and the min. So I'm just dotting that in here. It'll be at y equals 0.5, or 1/2. The amplitude is the distance between that axis of the curve, or axis of the function, and the max. It's also the distance between the axis of the curve and the function and the min. And so that length there is 1.5. If you want to actually calculate it, A for amplitude, we use the lowercase letter a for amplitude, just like the vertical stretch, and those actually fit in with each other here when we get into our sinusoidal functions more in depth. If we take our max and minus the min and divide by 2, so 2 take away -1 would actually be 3 divided by 2, which is 1.5, which is what we could see from the graph itself. We knew it was 1.5 units between the max and the axis of the curve, or between the min and the axis of the curve. All right, let's take a look at these and decide whether each function here is periodic or not, and if it's periodic, state the period and the amplitude and decide if it's sinusoidal or not sinusoidal. Now, we haven't talked about sinusoidal yet, so we'll avoid that question for now, and then we'll talk about it in a moment here. If it's periodic, so does it have a repeating pattern? So if we look at this very first one, can we trace out a repeating pattern like a stamp and then be able to replace that left and right? So if I look at that pattern, I think I then can trace that out again right here and so on. So yes, I would say this is definitely periodic. If I look at the length of one cycle, so if I go from here to here, this is 4 units and another 4 units, that's a period of 8. So the period equals 8 units. And then the amplitude. So I go from a high of 4 to a low of 0. That means my axis of the curve is here at 2. My amplitude would be 2. So the amplitude is equal to 2 units. It's the vertical distance, half the vertical distance of the entire thing, half the height. All right, the next one. We do have a repeating pattern. So I'm thinking kind of this check mark. But if I were to pick it up and stamp it over, I'd be going over this way. And so because it's actually heading upwards, it's not periodic. It does have a repeating pattern, but I can't just move it left and right. I would have to also move it up and upwards to get that pattern to totally repeat. So not periodic. The next one, if I look at that, can I trace out a pattern and repeat it? So I'm looking at that piece. And then can I repeat that? Can I go, yep, I think we can take that stamp, move it over, and then we could stamp again, and so on. So yes, I would say this one is periodic. And then if I look for the period, how long it takes to complete one full cycle, the way I've traced it out, it's kind of hard to see what the actual period is. So what I'm going to do is change my focus, and I'm going to go from this max value to this max value and see if I can figure that out. So this is a value of 1 here, and I'm heading over to here, which is 5. So that period is 4 units long. From 1 to 5 is 4 units. The amplitude, my minimum is down here at -1, and the maximum is up here at 3. So that's a total vertical distance of 4 units. So my amplitude is half of that. It's going to be 2. Again, well, that wasn't very creative of me. There we are. All right, so we're going to look at some actual real-life examples of where this all fits in. So many real-life situations can be modeled by these periodic functions. The hours in a day, the months in a year, the height of the water in a bay affected by the tide. So water comes in, tide goes up, water goes out, tide water level goes down in the bay. The height of a person riding a Ferris wheel is also periodic. You have a repeating pattern. So anytime you have that repeating pattern happening, you've got that periodic function. Lots of things on assembly lines, like tools that repeat a certain job over and over again, those would be periodic situations. So here's an example. The hours of sunlight in Windsor, Ontario are recorded for 2 years and graphed as shown. Day 1 represents about January 1st here. So we've got the hours of sunlight in Windsor and the number of hours on the y-axis, the day number of the since it's started to be tracked. What's the period of the function? So I want you to think about this. It's kind of hard to read based on our scale here. It looks like it's maybe going from here to here. So just over 350. If you think of hours of sunlight over the course of a year, that's going to repeat over and over again every year. So if we go with that, the period of the function should be about 365 because there's 365 days in a year. So it makes sense that it just repeats the pattern over and over again every year. The maximum number of sunlight hours based on this graph is roughly, I would say, about 15, and the minimum looks like it's at about 9 here. So 15 max and 9 is our min. What is the equation for this axis of the curve? So it's halfway in between that max of 15 and the min of 9. So looking at that, I could find the average. I could add those together and divide by 2, or I could just look at my graph and reason that out there. So that's going to give me 24 divided by 2, which is 12. So y equals 12 is where that axis of the curve is. What would that coincide with? So that equation would coincide with the days on which we have an equal number of sunlight hours to dark hours. So if you think of what we call those, we think of those as our equinoxes or equinoxes, the spring equinox and the fall equinox. So that's a little bit of geography pulling into our math course here. So these would represent our spring and fall equinox values. The max, that would coincide with our summer solstice, and the min would coincide with our winter solstice. All right, I did like geography. The height of a person riding a Ferris wheel is given by the graph below. What is the period of the function and what does it represent? So how does this actually fit into our real life? So you can see that we do have a cycle here. I'm just going to trace out a cycle. So it starts at the minimum height, goes up top of the Ferris wheel to the max, comes back down, the rider comes back down and is at the min, and then it's going to repeat again. So it looks like it takes 20 seconds for that full cycle. That one revolution of the Ferris wheel takes 20 seconds. And with the magic of technology, that's what I have written there. The period is 20 seconds, and it tells us that one revolution of the Ferris wheel takes 20 seconds before the rider goes around another time. What is the equation of the axis and what does it represent? So it looks like we have a maximum of 9 meters. Maximum height is here at 9, and the minimum is down here at 1, and that's so that you don't hit your feet on the ground or bang the ground on the way around. So you got to have a little clearance there. So that means halfway between 1 and 9, 1 plus 9 is 10, divided by 2 is 5. So our axis of the curve would be y equals 5. Okay, so the equation of the axis would be y equals 5, horizontal line. What it represents, that would be the height of the center of the Ferris wheel. That rotation point of the Ferris wheel is going to be 5 meters above the ground, because at 5 meters, you're going to be level halfway in between the max value and the min value. So it's going to be where that axis of the curve, the axle of the Ferris wheel would be. And then what is the amplitude and what does it represent? So we need that vertical distance between that axis of the curve and the max, or the vertical distance between the axis of the curve and the min, or half of the total height between those two things. So if I go from 5 up to 9, that's a difference of 4 units, or if I'm at 1 and go up to 5, again, that's 4 units. So in this case, if you think of the axle or the center of the wheel being 5 meters, and then the lowest point is 4 meters below that, that really represents the radius of the Ferris wheel. That radius is 4 units, or 4 meters in this case. So our amplitude is representing the radius of the wheel. The radius would be 4 meters for this. So if you were to think of, and I'm really bad at drawing, but I'll try my best. There's our Ferris wheel. Here's the axle, the center of that wheel. Here's the ground itself. This distance between the minimum, that is 1 meter in here. This radius, let me use a different color. This radius would be 4 meters. That means the center of the wheel is 5 meters above the ground. So hopefully that is making sense. This is a special type of function called a sinusoidal function. A sinusoidal function has this nice smooth curve that we have in this particular example. The example above was also sinusoidal. The ones prior to that, the three on the bottom of the first page, none of those were sinusoidal. They didn't have that continuous smooth up and down curve like this. But we'll define what sinusoidal means in our next video.